This is section 11.1, the ellipse. Let's go ahead and talk about conic sections and how their names were derived. And as you can see, what we have is something called a double napped cone. Each one of these is a double napped cone. And that's where these conic sections get their names. Let's first look. We have a circle, and as you can see, that is a horizontal cross section of the cone. An ellipse, if it's not horizontal, it's at any angle, as you can see, we will have an ellipse. The hyperbola is a vertical cross section through the double napped cone, and you can see that that is the hyperbola. And then at an angle not intersecting one of the cones, we have the parabola. So let's talk about how to graph an ellipse that is centered at the origin. So we will define an ellipse as the set of all points x, y in a plane such that the sum of the distances between that point and two fixed points is a constant. And these fixed points are called the foci, which is the plural of focus. And those are the foci of the ellipse. Now, the line through the foci intersects the ellipse at 2 points called the vertices. And the line segment with endpoints at the vertices is called the major axis. So let's take a look at these here. So if we have these vertices right here, and we have this line that has endpoints at the vertices right here, this line. This is called the major axis. Then we have a line segment perpendicular to the major axis, which is right here. I really wanted to switch colors to green. Perpendicular there, and that is the minor axis. So it's the major axis that has endpoints at the vertices, that line that has endpoints at the vertices. So technically, I probably shouldn't have drawn that like that. There we go. Right there. Major axis. And their endpoints are the vertices, okay? So, and these fixed points are the focus points, and these are fixed points, and they are the foci. Okay, so we have the major axis, the minor axis, and the center of the ellipse is the midpoint of the major axis. So the midpoint of the major axis is the center of the ellipse. Now we have some standard forms of the ellipse, the equation of the ellipse. So let's go ahead and take a look. We assume, this is pretty important, we assume that B is greater than 0 but smaller than A. So we assume A is the largest. Okay, so now let's go ahead and take a look. The major axis is going to have a length of 2A, and the minor axis is going to have a length of 2B. Okay, so here's the equation. If you have a major axis, which is the x-axis, your equation will look like this. The larger number squared will be under the x squared. If your larger number that is squared, and it will be then the larger numbers under the y squared, the major axis will be the y-axis. So that's how you know what the major axis will be, either the x-axis or the y-axis. And keep in mind, these are the ellipses centered at the origin. Okay, so here's your center. And now you can see the foci. And you can come up with these. C squared equals a squared minus b squared. And we'll be working these out. And so if the major axis of the ellipse is the x-axis, your foci are C0 and negative C0. If your major axis is the y-axis, your foci is 0, C and 0, negative C. And you can see that right here. And there's the y-axis. So this is major axis is the y-axis. And here, our major axis is the x-axis. Okay, so here's our vertices, which are the endpoints of the major axis. And these make a lot of sense because you can now see that the vertices here have 0 as their x-coordinate when you have a major axis as the y-axis. And you can see here that the coordinates of the vertices will have a y value of 0 when you have the major axis as the x-axis. And here are the endpoints of the minor axis. And here's the graph. And these are really nice. And every single point on the ellipse satisfies this equation. So we have a major axis as the x-axis because this is larger. A is larger than B. Okay? And so here we have the major axis as the y-axis. Whoops, I wanted to have that as here. There's our major axis. And in this case, as you can see, A is bigger than B. And this time, it's under the y-squared term. Okay. So that's a nice little summary. But let's try to work with these ellipses a little bit. Okay? So we'll go ahead and begin with this first equation. And as you can see, they've asked us to graph the ellipse. And what do you notice? You should notice here that 25 is larger than 4. So we know that a squared, because that's going to be the larger number, is 25. And b squared is going to be equal to 4. Okay, so the larger number is always a squared. Now, let's go ahead and solve these. A is equal to 5 and B is equal to 2. So we are taking the positive square roots of these numbers. Now, let's go ahead and compute C. C squared is equal to A squared minus B squared, which is 25 minus 4, which is 21. So C is equal to root 21, which is about equal to 4.6. Let's go ahead and compute our foci. Now, as you can see right here, let's look at our foci here. And we have our major axis. Let's write that. Major axis is the x-axis. That's because this 25 is under the x squared term. So let's go ahead and look this here. If the larger number is under the x squared term, we have the x-axis as the major axis. And as you can see, the foci are C0 and negative C0. So the foci are the square root of 21, 0. I don't know why I wrote those in that color. And then we also have negative root 21, 0. Okay? So those are the foci. And then our vertices, as you can see, we will go ahead and use our A value. So if you look here to look at the vertices, we're always going to have A in our vertices, okay? Now it depends on whether we are having an axis as the x-axis or if the major axis is a y-axis. But in this case, we will have A0 and negative A0 as our vertices. So that's A0 and negative A0. So let's go ahead and see if we can plot these points. So we'll go ahead and have negative 5, 0 and 5, 0. And then we can have our center at the origin. And then we have our foci. So that's the square root of 21, which is about 4.6. So we'll put those here. So 4.6, about right here, and about right here. And then we'll go ahead and find the endpoints of the minor axis, and the endpoints of the minor axis, I'll go ahead and write them. And that's going to be 0, 2, and 0, negative 2. And that would be B. So you can see here 0B and 0, negative B. So placing those, we would have 0, 2 and 0, negative 2. And that gives us this beautiful ellipse. And I can try to get it to fit here a little bit better. I think that's probably good. Not drawn very good. Let me try to delete that and do that one more time. There we go. That looks good. And there you have it. Okay, let's try another one. So here our major axis was the x-axis. Let's see what we have here. This isn't the form that we're used to. And we need x squared and y squared in the numerator. So what we could do is we could divide every term by 441. And again, as you notice, we need a 1 on the right-hand side. Let's look up here. There's a 1 and there's a 1. So we need to get that form. So if I divide every term by 441, that will give us 1 on the right-hand side. And we end up with x squared divided by 9, and I can show you that on the calculator, plus y squared divided by 49 is equal to 1. So actually on your calculator, you would put 49 divided by 441 and then click Math Frac. Okay. And I can go ahead and pull that up if we need to be. Okay, what do you notice here? You notice here that this time a squared is under the y squared term. A squared is always the largest number. So we have a squared equals 49, and we have b squared equals 9. So a is equal to 7, and b is equal to 3. And this time, our major axis is the y-axis. So, of course, we have our, did I write the center? I really wanted to make sure you all know that the center is 0, and I should have written that. Okay, so we have a center of 0. Now we can go ahead and compute c squared is equal to a squared minus b squared, which is 49 minus 9, which is 40. So c is equal to the square root of 40, which is equal to 2 root 10, and that's about equal to 6.3. That will help us for graphing. So now our vertices this time are 0, negative 7, and 0, 7. Our foci are 0, 2 root 10, and 0, negative 2 root 10. Okay, and then we talked about the endpoints of the minor axis. Let's go ahead and do that again. The endpoints of the minor axis. And remember that uses c, so we'll have c 0 and negative c 0. Whoops, that's not right. Supposed to be b. I was doing the foci. Okay, so we have b 0 and negative b 0. Okay, so let's go ahead and get these plotted. We have a center of 0. Our vertices are 0, negative 7, and 0, 7. And then our foci, I'll do those in a different color, and those are about 6.3. And then our minor axis. And then we should be able to go ahead and graph our ellipse. Here we go. Okay. So now this time we saw the major axis as the y-axis, and here in our first example we had the major axis as our x, as an x-axis. Okay, now what if the center is not 0? What if we have a center HK? How is that going to look? Well, they look very, very similar, and a lot of the rules remain. A is again greater than B, and if that larger number is under the x squared term, our major axis is horizontal, and otherwise it is vertical. And as you can see, here is H and here is K. So how do you know the difference? Which one is H and which one is K? So when A squared, when that larger number is under the x squared term, you can see that H and K are still in their correct place. So H is always that value after the minus sign under the x squared term. Okay, so if it's a positive, then it would be a negative. So as you can see, H is associated with the x and y, k, and that happens on both of them. So it doesn't matter where A is located when it comes to the center of the ellipse. Center is always HK. Now, if we're looking for the foci, and again, we will still use c squared equals a squared minus b squared. We will, of course, go to the right and to the left of H because the major axis is horizontal, or we will go up and down from K if our major axis is vertical. And the same things happen for these vertices and the endpoints of the minor axis. And you can see all of that here. So let's go ahead and start our first example where our center is no longer 0. And as you can see, our center is negative 2, 3, because this is x minus a negative 2. So we have negative 2, 3. Okay, as our center. Now we're going to pretty much do everything the same, but I would like to go place our center on this graph. So negative 2, 3, right there is the center. Okay. So let's identify A. Remember, A is the larger number. So A squared is 16. And then B squared is equal to 9. We have A equal to 4 and B equal to 3. We always want to go ahead and find C squared. And C is root 7. And yeah, so now we can go ahead and look at our vertices and look at our foci, okay? So let me just put this is about equal to 2.6. Okay, so now if we're going to go ahead and talk about our vertices, we're going to have negative 2, and we're going to add A, and we're going to have negative 2 and subtract A. And then, of course, we have that y coordinate of 3. So here we have 2, 3, and negative 6, 3. Okay, and then now we can go ahead and work on our foci. And here we have negative 2 minus root 7 and negative 2 plus root 7. And so we don't have to put those on there, but we could go ahead and compute that. So negative 2 plus root 7, that's about 0.6. And then we have negative 2, oh, that was the plus. And then negative 2 minus, we would have a negative 0.6, okay? And so I guess we could go ahead and put those on there. So negative 0.63. I don't know why that won't mark. And then we have 0.63. I don't think, let me take another look. Okay, so this was correctly written, but negative 2 plus root 7 is 0.6. And negative 2 minus root 7, I just didn't write this. It should be, because you could tell by the graph that that wasn't correct. It's negative 4.6. I think I just forgot to put that that 4 in front of that 0.6. Now that's better. So let me get rid of that. And so now these points are 0.63 and negative 4.6 would be about right here, 3. And that looks much better. Okay, the last thing would have to be what did we have here? The endpoints of the minor axis. So we're going to have H, and we're going to add and subtract B from K. So I think we wrote those as ends of, yes. So the ends of the minor axis, and we're going to have H, and then we're going to have K plus and minus B. So that would be 3. So that would be negative 2, 6 and negative 2, 0. So let's see what we have. Negative 2, 6 and negative 2, 0. And that looks pretty good. So let's go ahead and get this written. See if I can get this down here a little bit more. And bring that up. And it's about like that. Okay, that one was good. Okay, so what if we need to write the equation of the ellipse in standard form, and this is what we start with? Well, and we all know that form that we have to arrive at. We need a 1 on the right-hand side of the equation. We need the x squared in the numerator, the y squared in the numerator, a squared and b squared in the denominator. So we have quite a lot to do. Let's go ahead and take this step by step. So the first thing we're going to do is group the x variable terms and group the y variable terms together. So I'm going to have 9x squared, and then I'm going to go over here and I'm going to write a plus 5y squared. So I'm just going to go term by term. And then I have an 18x, and I don't have another, I do here, minus 30y. And then we're going to put this negative 9 on the other side of 0. So a positive 9 is a negative 9 on the other side of the equation. Or you could say that you're going to subtract 9 from both sides, okay? So basically, what we have now is an area where we're now going to factor out this constant term. And again, we're going to leave a blank. And then I might put another set of parentheses there. We're going to factor out a 5. And I'll put some parentheses here. And we have this. Now I'm going to create a perfect square. I'm going to complete a square. I'm going to create a perfect square by completing the square. Okay, so that's what we're going to do. So how are we going to do that? We're going to take this number 2, this first number 2, and we're going to take half of it. So 2 divided by 2, and we're going to square it, and that's 1. So we're going to add 1 here. So when you add 1 there, you're really adding how much? 9 times 1. So now we have to add 9 because we just subtracted, we had to add 9 to both sides, okay? So this is adding 9 to both sides, and then we added 9. I think that's the best way to explain it. Okay, let's do that over here. We're going to take 5. Let me erase this. We're going to take 5. We're going to take negative 6, whatever this b is. Divide it by 2 and square it. So that would be negative 3 squared is a 9. So this time we're going to add a 9. So what are we going to do now? So half of b and square it is what we add. Half of b and square it. Okay? So now, what did I just add to this side? I really just added, let me get that a little bit better. I really just added 45 to the right-hand side, so I have to add 45 to the left-hand side. So whatever you add to the right side, you have to add to the left side, okay? Okay, let's see if we can clean this up. We now have created this perfect square. Let's write our perfect square. So we have 9 times x plus 1 all squared plus 5 times, what is that, a y minus 3 all squared is equal to 45. So again, this is a perfect square. And this is a perfect square. We created a perfect square. Okay, so now what are we going to do? We're going to divide. We did this in the last problem. We're going to divide every term by 45. so that we have a 1 on the right-hand side of our equal sign. So 9 divided by 45 is 5, so we have an x plus 1 all squared divided by 5. We have a y minus 3 all squared divided by 9, and that's equal to 1. So we did it. Here you can see that let me put that in a different color, a squared is 9. B squared is 5. So A is 3 and B is root 5. Okay, so now from there, we usually go ahead and find C. Real quick, let me just write root 5 is about 2.2. So now we have C squared equals A squared minus B squared. And C squared is 9 minus 5, which is 4. And now we have C is equal to 2. Okay, so now let's talk about the center. The center of this ellipse is negative 1, 3. Negative 1, 3. And we've already computed A, B, and C, so now we can go to the foci. And remember, we're going to have our major axis, and that major axis is going to be a vertical line. So we have a vertical line as our major axis. And I think that was written in the definition here. Major axis is vertical when that larger number is under the y squared term. Okay? So now we'll have negative 1, and this time to the k, we're going to go ahead and add C, and that's negative 1, 5. And then we'll also have negative 1, 3 minus C, and that's equal to negative 1, 1. And those are our foci. Let's go to the vertices. We have negative 1, and then here we have 3 plus A, and then negative 1, 3 minus A. And those we'll go ahead and put on right now. So negative 1, 0 and negative 1, 6. And then our foci, we'll put those on there as negative 1, 5 and negative 1, 1. Those are not on the graph, but of course it's nice to have those. And then how about the length of our minor axis? And actually here are the ends of our minor axis. Sorry, not the length. And of course, here we will go have a total distance of 2. We will add B, which is about 2.2, to H. So here we will have negative 1 plus the square root of 5 and still have K. And then we'll have negative 1 minus root 5 and still have K. And that comes up with, so if B is about 2.2, this is a negative 1.2, and that's a negative 3.2. And let's see how these look. So we have negative 1.2 and 3. And then we have, that should be a positive 1.2. So a positive 1.2 and a 3. And then we have a negative 3.2 and a 3. Now that looks good. And so, as you can see, we have an ellipse. It looks like about that. Okay, that's a little off, but not going to be perfect. Okay. And the nice thing that you can see here is, just for an example, is you can see that A is 3. So this total distance from here, let me get a darker pen, is going to be 6. And then this total width is going to be 2 root 5s. So it's twice B and twice A. So I thought that was kind of nice to have. Okay, now let's take a look at this next question. They've asked us to give the equation of an ellipse in standard form, and they give us our center, the focus, and the vertex. And they only give us one focus, so we'll be able to figure this out. So the first thing we need to do is put the center in. So we have x minus 1 squared and a y minus 3 squared. We know that using that center. Now we need a squared and b squared under each one of these. Now how do I know which is which? So I really shouldn't put where a and b are yet. So let's go ahead and at least write this. So this distance from the center here is going to be, so let's go ahead and put the center on this graph. So the center is at 1, 3. So if we are given a vertex at 5, 3, 1, 2, 3, 4, 5, 3, if this is a vertex, so however this ellipse is shaped, and that's a vertex, that's one of the sides. Let's look at the focus. We'll use a different pencil here. And we have negative 2, 3 there. So what do you notice? If this is a focus, this focus is either on the left or the right side of the center. So of course this happens to be the left focus, so there's going to be another focus over here. And really, I didn't want to do that in red. I wanted to do that in green. So the focus is at negative 2, 3. And as you can see, this distance here is 3. Okay? And so this distance here is 4. So what do you know for sure? We know that C is equal to 3. And we know that A is equal to 4. So we have both of those bits of information just from looking at the graph and getting those on there. So now, could we find B? Yes. We know that C squared is equal to A squared minus B squared, and C squared is 9, is equal to 16 minus B squared, and as you can see, B squared is 7. So if B squared is 7, let's look at the difference here. B squared is 7 and A squared is 16. Okay, so we know that we must have a horizontal line for the major axis. And if that's the case, then A squared goes and belongs underneath the x squared term. So 16 would go under the x squared term, and I could put, since major axis is horizontal. Okay, and so B squared, which would be 7, would go under the y minus 3 squared term. So I think putting it on a graph sometimes makes it a little bit easier. Okay, now let's go ahead and look at this next topic. Determine and apply the eccentricity of an ellipse. The eccentricity of an ellipse. So we will determine that and then apply that. So it is, the eccentricity of an ellipse is the degree of elongation of an ellipse. And it's actually measured by the eccentricity E of the ellipse. So E is the eccentricity of the ellipse. So for an ellipse that looks like this, with the larger number a squared under the x squared term, or a squared under the y squared term, for either one of these, E is equal to C divided by A. And of course, A, same things apply. A is bigger than B is bigger than C. C is always a positive number, and there's our C squared equals A squared minus B squared. So one thing that's really important to know is that E is always a number between 0 and 1. We do have a fraction, or what you could say is a decimal. So let's go ahead and look at number 6. If the foci are near the vertices, that is, A is only slightly greater than C, then the ellipse is more elongated. If the foci are closer to the center, then you have a more circular ellipse. So I think that's pretty interesting. But we're just here to determine the eccentricity of the ellipse. So let's write this down. E is equal to C divided by A. As you can see, A squared is equal to 225, and B squared is equal to 9. So C squared is equal to, and let's go ahead and write what A and B are. So A is equal to 15, and B is equal to 3. C squared equals A squared minus B squared. That's 225 minus 9. That's 216. And so C is equal to the square root of 216. And that comes out to 6 root 6. We'll just go ahead and keep 6 root 6 so that we can come over here and place that value here for C. So now we have that E is equal to 6 root 6 divided by 15. And we can actually factor a 3 out of the numerator and denominator and have 2 root 6 divided by 5. So if you wanted an exact value for E, there you have it. And that's approximately equal to 0.98. Now, what do you notice? We have a very elongated ellipse. So let's compare A and C. So C is approximately, let's see what C is. 6 root 6 is approximately 14.7. And look at A. A is equal to 15. So when you compare A and C, you can see that A equal to 15 is only slightly greater than C. Therefore, we have a more elongated ellipse. And now I'm just going to move this over to the right, just so that I can have it here. Slightly, it's a little bit more elongated, okay? And so you can see that there. Now, let's look at another case. Let's go ahead and write our E is equal to C divided by A. And then over here, we have a squared equal to 9, b squared equal to 4. We have a equal to 3, b equal to 2, and c squared equals a squared minus b squared. So that's 9 minus 4. And so c is equal to root 5. And of course, we have the square root of 5 is about 2.2. We'll use that for comparison in just a minute. Put that up, okay? And so we'll take this c and place it here. So, and let me put a little dotted line or a little line between these problems. There we go. Okay, so now we have e is equal to the root 5 divided by 3. Now, root 5 divided by 3 is about equal to 0.75. And as you can see here, if the foci are near the center, and so that is going to be the case here, the foci is a little closer to the center, we know that we have a more circular ellipse. And here you can see that c is equal to 2.2. And of course, these are going to be a little bit closer to the center rather than just having a really, really close to that value. Okay. We could write that down. We could say ellipse is more circular. And that is since A and C are a little further apart. And you can see that here, A is 3 and C is 2.2. So those are a little bit further apart. Okay, now let's take a look at this next problem. Write the standard form of the equation of an ellipse with vertices -6, 7, and 2, 7. And here they give us our eccentricity of 3/4. Okay, so the very first thing we need to do, so this should be number 1. So number 1, we need to go ahead and write what the C is. Okay, the center is, and this center is going to be -2, 7. And -2, of course, is halfway between -6 and 2. So you can see this is 0, of course. So our distance between these are 8. So we'll go towards the center, 4. And 4, and that's the center. So you could say right there that that's -2, and that's the center, okay? So from there, we know that A is equal to 4. And how do we know that A is equal to 4? If we have the eccentricity is equal to 3 divided by 4. That is equal to C divided by A, okay? So A is equal to 4. So now we have our equation x plus 2 squared. And then we're using that center, y minus 7 squared. And now we need to decide whether we have the a squared under the x squared term or under the y squared term. And we need to determine what we have. So I probably should not have written this a equal to 4 yet, because what we have over here is c is equal to 3 and a is equal to 4. So with that, we can write c squared equals a squared minus b squared. and we have b squared equal to 7. So as you can see, a is 4, a squared is equal to 16. So we can go ahead and place 16 under the x squared term and 7 under the y squared term. And remember that the vertices are the endpoints of the major axis. So we do know that 16 will go under the x squared term since our major axis is horizontal. And that's why we have the 16 under the x squared term. So let me just move that over here. When I moved that, I didn't move the decimals. And there we go. Okay. Now, let's use ellipses in applications. So, this comet, Hyakutake, follows an elliptical path through the solar system with the sun at one focus. And the comet's closest approach to the sun is 0.2319 AU. And the eccentricity of this orbit is given by, and they give us here this decimal, 0.999784. And we are asked to find the distance from the comet to the sun at the point where it's furthest away. Now, AUs are astronomical units, and they are equal in a length equal to the approximate mean distance between the Earth and the sun. And as you can see, that is 92,955,807.3 miles. So let's go ahead and first begin with the value that they gave us. C divided by A is the eccentricity. They also gave us this distance, and that distance is A minus C, and that is the distance from the sun to the point on the right-hand side here. So let me just show you on this diagram. Right here, this is the distance from the major endpoint, the major axis endpoint, to the focus. And that focus is given right here of 0.23019, that distance. So we know that A minus C is 0.23019, and those are astronomical units. And then we were also given that E was equal to 0.999784. And we know that that's equal to C over A. And that's what we have there. So we know that C is equal to 0.999784 times C. Times A. Okay. So now with this, what can we do? We can substitute this value in here for C. So now we can say A minus 0.999784 A is equal to 0.23019. Just draw a line here. And we can go ahead now and combine those a values. And as you can see, we will have 1 minus that 0.99, and I can show you that on the calculator, is 2.16 times 10 to the negative 4a is equal to 0.23019. And if you divide both sides by 2.16 times 10 to the negative 4, you'll come up with a is equal to 1065.694. Okay. And now, if we want to find C, we can now take C is equal to 0.999784 times A, which is 1065,694. And we get C to be approximately 1065.46425. And now, guess what we have to do? We just have to go ahead and add A and C together. So A plus C is about equal, to 2131, or approximately 198 billion miles. That's pretty unbelievable. So if you converted that to billion miles. Okay, let's go ahead, and that's the distance from the comet to the sun. And you can see that right here, this distance right here. So we have a running track designed in the shape of an ellipse, 100 meters long by 50 meters wide. We're going to use a coordinate system with the origin at the center, okay? And we're going to, of the track, and a horizontal major axis. So that's important, a horizontal major axis. So we will have our larger value squared under the x squared term. And we need to write an equation for an ellipse. So if the running track is 100 meters long, that would mean 50 by 50 here. And if it's 50 meters wide, we have 25 and 25. So as you can see here, we have a squared is going to be equal to 50 squared. And b squared is going to be equal to 25 squared. And since we are centered at the origin, we have a squared centered at the origin and a horizontal major axis. We have a squared under the x squared term. And we could go ahead and multiply those out. 2,500, 625, and there you have it. Okay. Finally, we're going to learn how to solve this system. So we are wanting to find these two values right here. There's a point here and a point here where the line y equal to 2x, that's what this line is, intersects with this ellipse. Now, this ellipse is centered at the origin, and as you can see, a squared is equal to 16, and we do have a horizontal axis. The x-axis is the major axis. So we will have, go ahead and put here x squared divided by 16 plus, and now as you can see we have y equal to 2x. So we know that we have 2x all squared there, and 8 is underneath the y squared term, just so that you have that. B squared is 8. And we definitely have a, and since that's under the y-axis, we have a major axis as the x-axis. Okay, so let's go ahead and solve this for x. So it's going to take a little algebra, but we'll be okay. So we have x squared divided by 16 plus 4x squared divided by 8 equals 1. Now we will multiply every term by 16. Okay, so we have x squared plus 8x squared equals 16. And so we end up with 9x squared equals 16. And then if we divide both sides by 9, and we have x equals plus or minus the square root of 16/9, and we get plus or minus 4/3. So these are actually the coordinates of the solutions. We have 4/3, and we have a negative 4/3. So now we have to go ahead and use y equal to x, and we need to find the y value when x is 4/3, and then we have to find the the y value when y is negative 4/3. So we have 4/3, 8/3, and negative 4/3, negative 8/3. And that is the solution to the system. And that concludes this section.